requested to kindly maintain the digital etiquettes so that the session can run smoothly. And as the participants are joined from different institutions of India, so this session is divided into two segments. First one is the in the first segment, we will hear the views and ideas of our honorable guest, and the second one is the interaction session. If the participants have any queries, then they can put that in the chat box so that we can connect you to our honorable speaker. Now, I would like to invite introducer of today's session, Mr. Sanatan Kumar Mishra, who will introduce today's session. Sanatan, over to you. Thank you.
Thank you. Namaskar. A warm good morning to all of you present in the session. I am Sanatan, an undergraduate student of Central University of South Bihar. It is pleasant to welcome all the participants who have joined the session, ranging from IITs to prominent universities of science across India. Under this uncertain time, it is so warm to meet you all, and I pray for the same to continue. Mann Vivechan is an initiative by a student of Central University of South Bihar, and today, in its 24th session, we are excited to share the digital space with an eminent physicist of India, Professor Ajoy Ghatak. Beginning his higher education with Agra College, Sir has a full spectrum of experience built during his academic and research years. Ajoy Sir research area is fiber optics and quantum mechanics. He has authored and co-authored several books in this domain, which include Quantum Mechanics, Theory and Applications, Fiber Optics, Laser and Optical Electronics, and obviously one of his seminal work, Optics, which is phenomenal for learners like me and has been translated into multiple languages. His most recent work is on Einstein and special theory of relativity. Ajoy Sir unprecedented contribution in the field of optics and quantum mechanics has been recognized and celebrated in science community across world. He received the OSA 2020 Sang-Soo Lee Award for his seminal role in the development of fiber optics, guided wave photonics, and for pioneering optics education in India. Last year, he was awarded with Shastra G. N. Ramachandran Award for Excellence in Physics. Thirdly, it is optics which has made it possible for me to able to reach you. But the calmness and ease you brought every time we had conversation has actually made this session possible. Definitely, this house and I personally is much excited to hear you on topic and also receive word of insight and inspiration in disguise. Secondly, we are fortunate to have Dr. Puneet Mishra sir as moderator for this session, who is the faculty member and teacher of many of us present in the meeting, and including me. He has a specialization in condensed matter physics. And today we will have talk, learning, and insight. Meanwhile, I request you to kindly not unmute your mic unless I asked. Use chat box for questions, comments, and queries. In the interaction session, Puneet sir will help you reach to a speaker. Lastly, I welcome Puneet sir to officially start the session.
Thank you. Thank you, Sanatan. And so as Sanatan explained, I am Puneet Mishra, a faculty member from the Physics Department of Central University of South Bihar. And first of all, I would like to thank the team of Mann Vivechan for making me a part of this wonderful lecture to be delivered by Professor Ajoy Ghatak. And I'm really humbled. And we are really honored that Professor Ghatak has agreed to give this talk here. He is a great teacher and researcher par excellence, and it is hard to describe his contributions in physics research as well as physics education in words. He has a knack of explaining complex things in a very elegant and simple way, which is also evident from his textbooks on optics as well as in quantum mechanics, which most of us who are present here must be familiar with. So without any further ado, since we are all excited to hear his talk, I would like to request Professor Ghatak to please deliver his lecture. Over to you, sir.
Thank you, Dr. Puneet Mishra. And thank you, Sanatan, for, let me see. ये full screen नहीं हो रहा है. I am.
Sir, if you share your whole screen, then it will become full screen.
Stop. I have stopped presenting. Now I go back again, a window. ये क्या हो रहा है? Share. Can you see now?
No, sir.
Can you see?
Yes, sir.
Now I can see.
Okay. Thank you, Sanatan. Thank you, Dr. Mishra.
Sir, but it is still not full screen actually, I suppose.
It is not seen?
Not full screen yet.
तो आपका शायद बैंडविड्थ का प्रॉब्लम है, तो मैं ऐसा करता हूँ, इसको पीडीएफ कर लेता हूँ. चलिए, just 1 second.
Okay.
Oh, there must be some bandwidth problem.
I see.
Just 1 second. I'm converting that to PDF. That will have little less. Okay, now. ये क्या हो गया ये तो? हाँ. So this window. Can you see now?
Yes, sir.
Is it moving? Why study of light is so important?
Yeah.
Okay. This is in the PDF mode, so I will not have the animation. Chalo,
Okay.
once again, thank you for asking me to give this talk. It will be slightly mathematical, so let's see how things go. So I'm going to speak about brief history of light and evolution of quantum theory. Why study of light is so important? And from the study of light, the new field of photonics has emerged. And in fact, in 2015, UNESCO declared 2015 as the International Year of Light. Why did they do that? Because I'm trying to tell you the importance of the study of light. Because 1,000 years back, in 1015, the great scholar Al-Hazm in Mesopotamia, which is now in Iraq, wrote the first book on optics. It was entitled Kitab al-Manazir. So because to celebrate that, UNESCO declared 2015 as the Year of Light. And in proclaiming 2015 as the International Year of Light, the United Nations recognized that applications of light science and technology are vital for existing and future advances in medicine, energy, information, communications, fiber optics, agriculture, mining, and numerous other areas. So study of light and photonics has become extremely important. Then, about 4 or 5 years back, UNESCO declared May 16th as the International Day of Light. So why May 16th? Because on 16th May 1960, the American engineer Theodore Myman carried out the first successful operation of the laser was done by Theodore Myman on 16th May 1960. To celebrate that, and last year we celebrated 60 years of the invention of the laser. Using focused laser beams, as you know, low power, say a few 10 milliwatt or something like that, you focus it because it's a very directional source. Very important devices have been created for industry. This is a photograph from RRCAT, Raja Ramanna Center for Advanced Technology in Indore, and in which a focused laser beam can drill through concrete. And then, as you all know, laser beams are used extensively for eye surgery. And then large number of laser beams can be focused to create temperatures which will millions of degrees Kelvin, which will result in generation of fusion power. The above photograph shows the setup at the Lawrence Liver Laboratory in the United States. It can deliver more than 500 trillion watts of peak power to the target. So maybe in the distant future, maybe 5 years from now, we can have a laser-induced fusion reactor. Then fiber optics, which is my own field of study, laser pulses propagating through millions of kilometers of optical fibers connect us across the ocean and has revolutionized communication. Now today we are sitting in Delhi, you are in Bihar or Kerala, or even in London or New York. You can see this almost free of cost. And that has been possible because of optics and photonics. Fiber optics, lasers which can be modulated with tremendous rapidity. And India has done quite well in this communication system. So we are not lagging behind. We have developed the fiber optic technology. Today with cell phones, you see, 20 years back, I would make a telephone call to Bombay, it will cost me 100 rupees for 3 minutes or 200 rupees. But now it is almost free. You can call anyone, your friend in Delhi or friend in Chennai or Bombay or London or something like that. You can make a WhatsApp call. So think, what has led to this? Optics and photonics. So this has become an extremely important area of study. Half of the 2009 Nobel Prize in Physics was awarded to Charles Cow for groundbreaking achievements concerning the transmission of light in fibers for optical communication. And then you have 2018 Nobel Prize in Physics for groundbreaking inventions in the field of laser physics. And Arthur Ashkin discovered that he got the half of the Nobel Prize for optical tweezers. Maybe someday I will tell you about them. And then these two, Gerard Mourou and Donna Strickland, got the 2018 Nobel Prize in Physics for their method of generating high-intensity, ultra-short, very small duration, femtosecond laser pulses, 10 to the power of -15. And it has revolutionized surgery. Fiber optic endoscopy has revolutionized medicine. So it is optics almost everywhere. And therefore, optics and photonics. What is the difference between optics and photonics? Photonics, what we do in electronics, we do it with electrons. In photonics, we do it with photons. Everything is replaced by photons. And so therefore, they are subjects of tremendous importance. And I'm going to spend the next 45 or 50, 1 hour on what is light and evolution of quantum theory. Now, these are the people who have played very significant role in that. Isaac Newton, Christian Huygens, Thomas Young, Maxwell, Heinrich Hertz, Einstein, Max Planck, Millikan. Einstein explained the photoelectric effect by using his quantum model. The quantum was introduced by Max Planck in year 1900, and Einstein's formula was verified experimentally by Robert Millikan, because of which Einstein got the 1921 Nobel Prize in Physics. Then came Niels Bohr, Arthur Compton, Compton scattering, Louis de Broglie, who said that the electron should also behave like a wave. And then Heisenberg, Schrödinger, Dirac, who formulated the quantum mechanics. So in 1925, quantum mechanics was discovered. And 3 years from now, we will be celebrating 100 years of quantum mechanics, which is a revolution, And I hope I live to see the celebration of 100 years of quantum theory. Sanatan, can you see the images of Newton, etc.?
Yes, sir.
Okay, good. I learned quantum mechanics from these two great teachers, Professor Daulat Singh Kathari. He was a Gandhian. He was a great man. And so was Professor R.C. Majumdar, who taught us in our master's course, Quantum Mechanics and Nuclear Physics at Delhi University. And I did my MSc in 1959, when probably your parents were not born. So Professor D.S. Kothari was a great human being, very simple. And we would all like to emulate him. We had great teachers. We were very fortunate to have great teachers. And therefore, we wanted to become teachers. Now the younger generation feels that they would like to do an MBA, which is also good. Here is Professor D.S. Kothari and myself. And I also had the privilege of learning quantum mechanics from Professor Hans Bethe, who, as you know, got the Nobel Prize in Physics. Someday I may tell you about that. And he taught us 2 courses on quantum mechanics. And he fled Nazi Germany in the early 40s. And he came to America and taught at Cornell University. And I did my PhD from Cornell. And therefore, it was a great experience to listen to him. So the references for today's talk this is Dirac's book on quantum mechanics, Feynman Lectures, Volume 3. Here is Feynman explaining something to Dirac. This is a very classic photograph. And then there is a very beautiful book on quantum theory by David Bohm. Here is David Bohm, and here is J. Krishnamurti. So David Bohm had very good interaction with J. Krishnamurti. And then there is another book, Quantum Mechanics by Cohen Tanuji. Here Cohen Tanuji receiving the Nobel Prize, which has been translated by Dan and Nicole Ostrowski. This is Nicole, this is Dan. They are my very good friends. And here is, on the back is myself. So there are large number of books on quantum mechanics, but I think these are the 4 classic books. No errors in any book, and written by Nobel Prize winning scientists. David Bohm did not get the Nobel Prize, but he deserved a Nobel Prize. He was Nobel Prize material. Whatever I will say today, I will follow my own book on optics, which has been mentioned. The 7th edition, I have written it, tried to write it very, very carefully. So that is the reference for today's talk. And the 6th edition of my quantum mechanics book, which I have written with Professor Lokanathan. Here is Professor Lokanathan. This is myself, long time back, about 30 years back. So this is the start of the talk. That was just a preamble. Isaac Newton put forward the corpuscular model of light, and in his book on optics, which is spelled as with a K there, are not the rays of light very small bodies emitted from shining substances? So very small corpuscles are emitted from shining substances, and using the law of conservation of momentum, he wrote down the Snell's law, and of course everyone admired Isaac Newton. So everyone thought that light was indeed in the form of particles. And if it were in the form of particles, it must cast a very sharp shadow. But in the shadow, if I can read a book, this is my book on optics, if I read a book, the light that enters is not because of diffraction, it is because of scattering of air molecules. So if you are in a shadow of a building, you can still read a book. And that is because of the scattering phenomenon. Scattering of light by air, by the nitrogen molecules and things like that. If you are on the surface of the moon, and let there be bright sunlight coming in, the shadows are pitch dark. That is because there is no atmosphere here. There is no atmosphere, very little atmosphere. So light, you see, it casts very sharp shadows, and so therefore light travels almost in straight lines. So that was, of course. Then around the same time as Newton, Christian Huygens put forward the wave theory of light. And that there is an animation here which I am unable to show because it is in the PDF mode. Waves spread out, like you have a calm pool of water and you make a pin go up and down, it will generate waves. What is a wave? It's a propagation of disturbance. The water molecules do not go here, they just transfer the disturbance from one point to the other. That is a wave. So what is a wave? A wave is, for example, you take a string, make it move up and down, then that is an X-polarized wave because the displacement is in the X direction. And displacement of each point of the string can be represented by this equation. So this equation, if someone asks you, what is the simplest wave? The answer to that question is this equation. If the displacement is given by cos kz minus omega t, then this equation defines a wave. And since the displacement is in the X direction, you have an X-polarized wave. If you move it horizontally, you have a Y-polarized wave. So you see, X of Z comma T is equal to so much. I take K outside, so I write down Z minus Vt, where V, when I have three equal to signs, it means defined to be equal to. V is defined to be equal to omega by K. That represents the velocity of the wave. How do I do that? Because at t equal to 0, it is a cos kz. If I put t equal to 0, then it is a cos kz. And at a slightly later time, it will be z minus v delta t, as if the origin has moved. So this is the displacement of the string at t equal to 0, and the dashed curve represents the displacement of the string at delta t, so that the whole disturbance has moved through a distance v delta t in time delta t. So therefore, I have proved that v, which is omega by k, represents the velocity of the wave. If I rotate the string in a circular motion like this, then I have what is known as a circularly polarized wave. In this case, if I rotate it in the clockwise direction, then you have a right circularly polarized wave. Each point on the string moves on the circumference of a circle. So as I mentioned, if I have a calm pool of water, I make a pin move up and down, and it will generate waves. And this is the distance lambda, with distance between two crests, which is equal to 2 pi by k. And omega equal to 2 pi nu, where nu is the frequency. I'm sure all of you are familiar with that because that is taught at the school level. So this is a very beautiful video which I had, which I'm unable to show, that if you have two pins moving in phase, then each sends out a wave. And if one produces of the water molecules produces a displacement like this, the other is out of phase, then the resultant will be zero. If one produces a displacement like this and the other also produces, then the amplitude will become twice and the intensity will become 4 times. So with waves, if you have two sources of waves, they will produce an interference pattern. So here is the actual interference pattern produced from 2 point sources vibrating in phase in a ripple tank. Ripple tank is you have a calm pool of water and you have 2 pins vibrating up and down. So you remember the wave theory was put forward by Huygens in 1650. Around that time, he wrote a very beautiful book. I have read the English translation of that book, very beautiful book. So Thomas Young, he was a medical doctor, and he carried out a very beautiful experiment. He had a huge screen or a cardboard in which he pierced 2 holes. And he allowed monochromatic light. And how did he produce monochromatic light? He allowed white light, the sunlight, to pass through a filter. And then he saw dark and bright fringes. And from this, as you all know, you can calculate the wavelength, which is the fringe width, beta is the fringe width, d is the distance between the holes, and capital D is the distance between the 2 planes. So because he could demonstrate interference fringes, light then appeared to be in the form of a wave. I must tell you one thing. Remember, the original Thomas Young experiment was not with 2 slits. Most people write 2 slit Young's experiment. No, it was with 2 holes. And you have almost straight line fringes. In fact, they are hyperbolic in nature. I've shown this very carefully in my book on optics, that actually with 2 pinholes, you get hyperbolic fringes. But if you replace that with this, but if you look at a small portion of the fringes, then they are almost straight line. So, sorry. So if you have a gun emitting bullets and you have this 2-hole interference pattern, so either the bullets pass through hole number 1 or hole number 2. So if hole number 2 is closed, you get this intensity distribution on the screen. If hole number 2 is open, then you get this. And if both holes are open, then you get P1 plus P2, because the particles will either come from here or will come from there. And there is no interference pattern. So interference pattern cannot be observed by means of a particle model of light. On the other hand, if you have a wave source, as I was mentioning, each hole generates waves which will interfere to produce this interference pattern. These photographs, these diagrams are adapted from the Feynman lectures. So if you observe the interference pattern, as Thomas Young did, and he could say, light plus light can produce darkness. This is actually Max Born who said this later, that what is the greatness of Thomas Young's experiment? It is one of the most beautiful experiments in science. Light plus light can produce darkness, and that is possible only if it is a wave. So quickly the wave theory was established, as you all know, and in the beginning of 19th century, diffraction experiments were performed, the wavelength was measured, and the wavelength was found to be about half of a micron for the yellow color. Micron is a millionth of a meter. You know, Thomas Young was a medical doctor, and people say he was the last man who knew everything. In fact, there is a book by Andrew Robinson, very nice book, The Last Man Who Knew Everything. Thomas Young, the anonymous polymath, who proved Newton wrong, explained how we see, cured the sick, because he was a he was a medical doctor, and deciphered the Rosetta Stone, among other feats of genius. Now, you know, men who know entire physics, people say, I have read this, that these days no one understands the entire physics. Physics has become so vast. But the two people who knew completely physics were Richard Feynman and Landau. Some of you may have read the books by Landau. So light was established as a wave. As you know, when the sunlight comes to the earth, then it passes through vacuum. But wave requires a medium because it has to transfer energy from one point to the other using water molecules. Let us suppose you are in front of me, and if there is no air, then you cannot hear me. Let me have a little bit of tea. My throat is not too good. So how could it propagate through vacuum? So around the same period of time, laws of electricity and magnetism were getting discovered. Michael Faraday, as you know, is a great man, a great physicist. So he discovered Faraday's law. What is Faraday's law? If you have a magnet, you move up and down, it generates a current. A changing magnetic field produces a current. Maxwell wrote this law in the form of an equation. So this came to be known as Faraday's law. It is an experimental law. It cannot be derived. It is an experimental law. It cannot be derived. So he derived this equation, and it physically implies that a changing magnetic field, delta B by delta T, is changing magnetic field produces a changing electric field. And that was Maxwell's contribution. But it was Maxwell's contribution, meaning that he described the Faraday's law in the form of an equation. Then came Ampere's law, that a current passing through a conductor produces a magnetic field. And Maxwell also wrote this in the form of an equation. And he wrote that curl of H is equal to J. So these are the two very famous equations that Maxwell wrote down. But then Maxwell did something beautiful, something extraordinary. He said that not only a current produces a magnetic field, but a changing electric field also produces a magnetic field. So he introduced in Ampere's law, this is Ampere's law, he introduced another term, which is delta D by delta T, which is known as the displacement current. So it is not only a current which produces a magnetic field, but a changing electric field also produced, like between the plates of a capacitor, that also. An introduction of this term, which was Maxwell's great contribution, revolutionized physics. He just wrote it down so that this equation becomes, so it cannot be derived. So that this equation, if you take the divergence of this equation, then you get div curl H is equal to 0. So divergence of J plus delta by delta T of divergence of D, which is rho, which is the equation of continuity. Maxwell's equations cannot be, they are experimental laws. And the entire field of electricity, classical electricity and magnetism, understand this, entire field of classical electricity and magnetism are just solutions of Maxwell's equations. Entire field are just the solutions of Maxwell's equations. So now let us see. Now understand this very carefully. Slight amount of mathematics, but it is truly beautiful. So this is Faraday's law. E is the electric field, H is the magnetic field, and mu0 is equal to 4 pi into 10 to the power of minus 7. So I assume a wave-like solution for the electric field. I substitute and calculate the curl of the E vector, then integrate with respect to time. You please do this. You take this as the expression for E, substitute it here, and you find the value of H. So this, as I told you, this represents a wave. So understand what Maxwell did. He said that wave-like solutions of the electric and magnetic field are solutions of Maxwell's equations, or the laws of electricity and magnetism. And so therefore, he predicted, understand my word, predicted the existence of electromagnetic waves, that electromagnetic waves must exist. And this is proportional. The H is proportional to E0. So a changing electric field will produce a changing magnetic field, and a changing magnetic field will produce a changing electric field. So this is the X-polarized. I'm assumed a X-polarized electric field. Then you will have in the magnetic field in the H, in the Y direction. The concept of electric and magnetic fields were introduced by Michael Faraday. It's very important. Today we take it for granted. For example, you take two charges. Before Faraday, they knew that this charge will attract this charge or repel this charge. So force of attraction. What Faraday said was that if you have an electric charge sitting in empty space, it produces a field, electric field. So that is present even in vacuum. If you put another charge there, it will experience an attractive or a repulsive force. So the concept of the electric and magnetic field, which today we take for granted, was introduced by Michael Faraday around 1845 or something like that. Now, these are the two solutions we have. What we do is we substitute this in the law which was modified from Ampere's law. We had Faraday's law and Ampere's law. So now in Ampere's law, we introduced the displacement current. This is the displacement current. So I substitute this and this in this equation. And I would like all of you to do that. I'm sure most of you have done this. Then you will find it's a little algebra. Omega by k comes out to be 1 over a mu naught epsilon naught. You substitute the values of mu naught and epsilon naught. and you get 300 million meters per second. So understand what Maxwell did. Maxwell said that from the law, he put the laws of electricity and magnetism in the form of equations. And these equations cannot be derived. He put the laws of electricity and magnetism in the form of equations. And then he said that wave-like expressions for electric and magnetic field are solutions of that equations. And so therefore he predicted the existence of electromagnetic waves. And he said that the velocity must be around 300 million meters per second. And this was the velocity, about 310 or something like that, million meters per second, was measured by Fizeau in 1849. And he said, these two numbers cannot be accidentally equal, and so therefore light must be an electromagnetic wave. That was one of the greatest syntheses in the development of science. And Maxwell is considered as one of the greatest scientists of all times. So what he did was, I'm sure most of you are aware, he wrote down the waves, and he said these waves must have this velocity, must have this velocity. Ye hona chahiye. And there he found that this is close to the velocity of light. And so therefore he said, light must be an electromagnetic wave. His exact words were, with faith in rationality of nature, that these two numbers cannot be accidentally equal, I propound that light must be an electromagnetic wave. So this is a great synthesis. The two subjects, electricity and magnetism and optics, are part of the same framework. So around 1864, Maxwell, in his famous book, A Treatise on Electricity and Magnetism, predicted the existence of electromagnetic waves and said that light itself is an electromagnetic wave. An oscillating electric field produces an oscillating magnetic field, an oscillating magnetic field produces an oscillating electric field. That is how the fields propagate through vacuum. So there is no ether. You don't require a medium. Because once you have an oscillating field, let us suppose I have an electron, I make it move up and down. So the field also changes. So a changing electric field will produce a changing magnetic field, and these fields will propagate. And God said, this is again quoting Feynman, let there be Maxwell's equations, and there will be light. Then this was done in 1864. In 1887, Heinrich Hertz generated electromagnetic waves of much shorter wavelength. He created a stationary wave, measured the wavelength, he knew the frequency, determined the velocity, and he found that that was about 300 million meters per second. So Heinrich Hertz was the first who generated electromagnetic waves using electromagnetic circuits and things like that, antennas and things like that. As you all know, now we know gamma rays, X-rays that you use in diagnosis, ultraviolet, infrared, microwave ovens you have, radio waves that you receive on your cell phone, they are all electromagnetic waves. And this visible region occupies a very small region of the electromagnetic spectrum, and all wavelengths travel in free space with an identical velocity of 299,792,458. Isko yaad rakhna. Remember this. Meters per second. So that was a great synthesis that was put forward. So Max Planck later said, Maxwell's theory remains for all time one of the greatest triumphs of human intellectual endeavor. You could, with Maxwell's theory, you can reflection and refraction propagating through solids and liquids and everything. You must have read that in your solid state physics book or your electromagnetic theory book. You can do everything. So therefore, people said that in 1894, the famous British physicist, Lord Kelvin, you measure temperature in kelvins. So he said that there is nothing new to be discovered in physics now. All that remains is more and more precise measurement. And then came Einstein. So in the year 1905, Einstein published 5 outstanding papers. These 5 papers are often referred to as the Annus Mirabilis papers. Annus Mirabilis are Latin words meaning miracle year. So the year 1905 was Einstein's year of miracles, when he was alone, not in an university, not in a big university, not in a research laboratory, but in a Swiss patent office, where he worked very hard and produced those 5 outstanding papers. There is a beautiful book. Get it for your library. Einstein's Miraculous Year, 1905. 5 papers that changed the face of physics. It gives the 5 papers and gives the description of the 5 papers and the English translation of the 5 papers. In the first paper, Einstein described a new method for determination of molecular dimensions. In the second paper, it's a small video which I am unable to show. He gave the theory of Brownian motion, that you have a large particle like a virus or something like that is hit by, say, molecules of water or something like that, and it will move. It will move. It's a very beautiful video. So he gave a theory of that. And in the 4th paper, I have missed the 3rd paper. In the 4th paper, he gave the theory of relativity. And in the 5th paper, someday I will tell you about E is equal to mc square. That's a very beautiful contribution that Einstein made in his year of miracles. What does this equation mean? I have my own derivation of E is equal to mc square and the consequences of that. So in the second paper, in his year of miracles, Einstein wrote that light, this is the English translation of his original German. Radiation energy means light energy, consists of indivisible quanta of energy, packets of energy. And what is the energy? Equal to h nu, where nu is the frequency, h is the Planck's constant, and it also has a momentum. In a later paper, he showed that it also has a momentum equal to h nu by c. This was a revolutionary concept. This was something similar to Newton's particle model. No one would believe Einstein. No one would believe Einstein. And this was a revolutionary concept. That is, light comes in packets of energy, not in the form of waves, which eventually led to the development of quantum theory. So this is if someone asks you, who discovered wave-particle duality? Einstein in 1905, because he says that you have Maxwell's electromagnetic waves, which explain light very beautifully. Then you have the particle model. And using this, he derived this equation. This is known as the Einstein equation. You allow ultraviolet light to fall on this plate. You have electrons coming out. The maximum kinetic energy of the emitted electrons is equal to h nu minus a constant. A constant depends on the plate. This constant, if it is sodium, it has some value, it has potassium, it has some value, and so on. So there is always a critical frequency. And this was observed this has experimentally been observed before. And Einstein said that you can explain this in the form of a particle model of light. this was this was verified experimentally by Robert Millikan. I must tell you, Einstein did not get the Nobel Prize for his theory of relativity, nor for the concept of the light quantum. But he got the Nobel Prize for this Einstein equation. This equation was put forward by Einstein in 1905 and was experimentally verified. He measured the kinetic energy of the electron, and he said that the Einstein's equation is almost exact. So Einstein received the 1921 Nobel Prize in Physics for this equation, and Robert Millikan got the Nobel Prize for the experimental verification of that equation and also for photoelectric effect. William Oswald, who won the 1909 Nobel Prize for Chemistry, was the first to nominate Einstein for the 1910 Nobel Prize for his theory of relativity. So year after year, he was getting nominated. So you think there is politics in Bihar, there is politics everywhere. And he did not receive the Nobel Prize. Einstein had put forward the general theory of relativity, which predicted the bending of light by stars. And this was observed by Arthur Eddington. Arthur Eddington verified general theory of relativity during the 1919 solar eclipse. This is the 1919 solar eclipse. This is the actual position of the star. And looking from the Earth, this is the Earth, you see it slightly raised. And he calculated this angle. Einstein calculated this angle from his general theory of relativity, which was verified experimentally. So his theory was verified, but neither did he get it. There is very beautiful history on the award of the Nobel Prize. In 1922, Einstein received the 1921 Nobel Prize in Physics for his explanation of the photoelectric effect, and not for his theory of relativity, not even for the concept of the photon. So this is the actual medal that was received by Einstein. As you can see, Einstein's name is written there. But he gave the Nobel lecture on relativity at Gothenburg. There's this beautiful book on politics of excellence by Friedman. I have written a book on Einstein, The Story of a Genius. It's a glimpse of his life. So then came a Compton in 1923. He carried out, as you all know, Compton scattering experiment. A photon coming in, getting scattered to a different frequency. And using these two equations, which were put forward by Einstein, and simple conservation of energy and momentum. So the photon comes in, gives some energy here and gets scattered. Packets of a slightly different energy. That is, frequency is slightly different. And he calculates that. It is given in every book, including my own book on optics. And he calculated this, the scattered wavelength, compared with his experimental data, and he found that it fitted very nicely. So it was only after 1923, after Einstein got the Nobel Prize, that the concept of the photon was established. So this resulted in the wave-particle duality. Arthur Compton received the 1927 Nobel Prize in Physics. This is the wave-particle duality which led to quantum theory. Then in 1897, J.J. Thomson discovered the electron. Now we know the electron's mass to 10 decimal places. Electron charge to 10 decimal places, very accurately. So how do I visualize this electron? As a tiny particle, because it has a certain mass. It has a certain charge, and It can be deflected by an electric field. It can be deflected by a magnetic field. Oh, what is this? Kya ho gaya? This is the wave-particle duality which led to quantum theory. Then Louis de Broglie said that P is equal to h nu by c is equal to h by lambda is the momentum of a photon. He said this electrons should also behave like waves. This was the prediction made by Louis de Broglie. That's why he became so famous. So he said that this equation should be valid even for electrons. And he justified it by saying that at that time Niels Bohr had put forward the Bohr model of the atom, which you study. And in the Bohr model of the atom, the angular momentum is quantized. MVR is the angular momentum of the electron, is equal to NH by 2 pi. So therefore 2 pi r is equal to NH by MV. MV is the momentum, NH by P. So he says that 2 pi r must be equal to n lambda. So these are the stationary states. So he justified his de Broglie wavelength from Bohr's, using Bohr's model. Quantum mechanics had not discovered. And it was, Niels Bohr had come to Delhi University in 1959 or 60. And there is myself. I was at that time, a long time back, I was a young man. This is Niels Bohr, this is Professor Aulak, Professor Majumdar, Professor Mitra. It was a great visit. So we had the privilege of listening to Niels Bohr. So Louis de Broglie received the 1929 Nobel Prize in Physics for his discovery of wave nature of electrons, which was verified later. That is the most important point. De Broglie predicted it in 1924, and it was experimentally observed by Davison and Germer in the United States, and G.P. Thomson, son of J.J. Thomson. This is the diffraction pattern by an aluminum foil produced by X-rays, and this is by electrons. Now, this is the diffraction pattern, which is due to the wave nature of X-rays. They are similar. They are almost identical. So, jo ye hai, wo ye bhi hai. Whatever, if it is a wave and particle, whatever it is. So, this experiment finally established that electrons also have a dual nature, because of which Davison and Thomson shared the 1937 Nobel Prize in Physics for their experimental discovery of the diffraction by electrons. And Germer left out. Germer was not given the Nobel. So now the most important part comes. Is the electron, listen to this very, very carefully. Is the electron or a proton a wave or a particle? Some books write that it is sometimes a wave, sometimes a particle. Some books write it is a wave and a particle. The correct answer is they are all wrong, all incorrect. The correct answer is, as quoted by Feynman, that they are neither waves nor particles. Waves bhi nahi hai, particles bhi nahi hai. So then the question that you will ask me is, then what are these? I'm quoting Feynman because if I had said that, probably you will not believe me. But Feynman in his book writes very beautifully that they are neither waves nor particles. This is very important. Then what are those? And the answer to that question is, listen to this very carefully. They are described by the wave function psi. What is an electron or a proton or a neutron? Quantum mechanics describes it with a wave function psi. And what is psi? It is the solution of the Schrödinger equation. Then you say, how did you write that down? So Feynman again writes, where did we get that equation from? The answer is nowhere. It is not possible to derive it from anything you know. It came out of the mind of Schrödinger. How beautiful. It sums up the entire quantum theory. That what is the wave function psi? So I said three very important sentences. Number one, what is an electron or a proton? It is neither a wave nor a particle. Then what is it? It is described by the wave function psi. What is psi? Psi is the solution of the Schrödinger equation. So you will say, where did you write it from? So it came from the mind of Schrödinger. So as I told you, Schrödinger equation cannot be derived. Quantum mechanics cannot be derived from classical mechanics. Maxwell's equations cannot be derived. So I've told you a few very important things. So this is so beautiful that women have painted on their back. So here is a derivation, heuristic derivation. This is not a rigorous derivation. This is not a rigorous derivation. I take a plane wave and then I introduce the de Broglie relation, P is equal to h by lambda, which is equal to h by 2 pi into 2 pi by lambda h cross k. So k is equal to p by h cross, and Einstein relation is E is equal to h nu is equal to h cross omega. So omega. So I substitute for k p by h cross here, and for omega E by h cross here. And I get for a plane wave describing an electron. And I know for a free non-relativistic particle, E is equal to p square by 2m. So I substitute p square by 2m here, and I get this equation. And I differentiate with respect to time. So p is now a number. So I get I by h cross minus p square by 2m multiplied by I h cross, which is p square by 2m times the whole thing, that is psi. And I differentiate this twice with respect to x and multiply by h cross square by 2m. If I differentiate with respect to x, then I get I by h cross into p whole square, that is minus p square by h cross square. H cross square cancel out, minus minus plus p square by 2m. So the right hand sides are equal, and I get this equation. So I have given a very hand-waving argument to arrive at the Schrödinger equation. Each book has its own way of getting to the Schrödinger equation because it cannot be derived. So this is the one-dimensional Schrödinger equation. So now I don't ask as to how I have got this. I now solve it for a free particle and use the method of separation of variables and so on. And you get this as the most general solution of the Schrödinger equation. So if you have to understand quantum theory, you have to do a little bit of mathematics. Arey, Dr. Mishra, it is 11:04. Oh my God. So what should I do? Have the students disappeared or they are there or what?
No, they are there, sir. They are there. They are listening to you, sir.
So
We're here, sir. We're here.
So 10 more minutes, 15 more minutes?
Sure, sir.
Yes, sir.
Okay, so this is the most general solution of the one-dimensional Schrödinger equation that I wrote, where p is a number which goes from minus infinity to plus infinity. So this is the solution of the Schrödinger equation. And okay, let me go. Then 1926, Max Born gave the following physical interpretation: psi squared dx represents the probability of finding the electron between x and x plus dx, and P of px dpx is the probability of finding the momentum of the electron between P and P plus dp. Listen to this carefully. Classical mechanics is deterministic. Quantum mechanics is probabilistic. That is the conceptual difference between classical mechanics and quantum mechanics. And okay, I'll skip this, otherwise it will. So I have psi of x comma t. This is the solution of the Schrodinger equation. At t equal to 0 becomes this. So if I know psi of x comma 0, then I take the inverse Fourier transform and I get this. All the details have been worked out in my optics book. I have worked it out for those who are interested. So if you have a particle described by a Gaussian wave function, so then you describe this. So the probability distribution is about sigma naught. Then if you calculate the Fourier transform of that, A of P, then the spread in momentum is h cross by sigma naught. So you write down, so you get delta x delta p is of the order of h cross. So if the particle is local, so understand this, uncertainty principle is contained in the solution of the Schrodinger equation. It doesn't come from above. Uncertainty principle is contained in the solution of the Schrodinger equation. It was put forward by Heisenberg in 1927. And so therefore, skip karte hain. So let me conclude by these two experiments. I will take 5 more minutes. I now want to do the single slit diffraction experiment. And if you do the diffraction of waves, then this is my Fraunhofer diffraction of waves, which is given in any book on optics, where beta is equal to pi b sine theta by lambda. B is the width of the slit, theta is the angle of diffraction, lambda is the wavelength. You must have all done this. Sometimes you do this in high school, that this is the Fraunhofer, a plane wave coming in a slit of width b, it spreads out. You now solve the Schrodinger equation for that. So you assume that the electron is described by a wave function, which is here. And then using this, you calculate the momentum distribution function. And you find that because it is confined within a distance of b, its momentum distribution is the same as the intensity distribution in the classical wave theory. So therefore, this is classical wave theory, intensity distribution, and quantum mechanics gives probability distribution. So you have diffraction of single electrons. So single electron, which has a very accurately determined mass and momentum, it comes in, it interacts with the slit. The slit imparts a momentum. The slit, understand, the slit imparts a momentum. But how much momentum? The answer is, I don't know. The quantum theory gives a probability distribution. ये screen पर कहाँ आएगा? Where will it land up? I don't know. I can only predict a probability distribution. So as I said, classical mechanics is deterministic. Quantum mechanics is probabilistic. So, and again, the momentum that is imparted is consistent with the uncertainty principle. So I have solved the Schrodinger equation. You have to work out the steps. Please do that. All the details are given in the 7th edition of optics. I have done this very, very carefully, and it is not given in many books. It is given in some books. Then finally, I do the double slit experiment, Young's interference experiment. As you know, the wave theory classical wave theory, which is given in my optics book, any book on optics, it's given by this. This is the single slit diffraction pattern, Fraunhofer diffraction pattern, and this is the 2-point interference pattern, where beta is equal to pi b sine theta by lambda. B is the width of each slit, theta is the angle of diffraction, and gamma is pi d sine theta. D is the distance between the two slits. Now you do the corresponding quantum mechanics of it. That the electron, this is the beautiful part. Electron now passes through both the slits at once. Does it become half and half? No, no, no. It never becomes half and half. Electron is described by a wave function. Do not think that it is a particle. Do not think it is a wave. It is described by a wave function, which is here as well as here. So it passes through both the holes at once. And how does that electron pass through both the holes at once? No one understands. And then you find the probability distribution, and little algebra will show that the probability distribution is the same as the intensity distribution. So you see, I have an electron gun and I want to do the interference experiments. So you believe that electrons are in the form of bullets. It passes through hole number 1 or hole number 2. No. So if that was indeed the case, you will get this as the intensity pattern. When both holes are open, the electron will pass through either hole number 1 or hole number 2. It is very beautifully written in Feynman lectures. But electron has a definite mass and a definite charge. So you feel that it should pass through one of the holes. But when you make the measurement, you do not get P1 plus P2. But you get the interference pattern. And how do you explain that? That electron is described by a wave function which is here as well as here. It passes through both the holes at once. If you make a measurement, it will be either through hole number 1 or through hole number 2. And the process of measurement will destroy the interference pattern. And then this is the most beautiful experiment in science. You do this experiment in one electron, then another electron, then another electron. So if you did this experiment with 10 electrons, you will get 10 spots. 100, 3,000, 20,000, and 70,000. This is the famous Tonomura experiment, which established the quantum behavior of the electron or the proton. And similar experiment has been done also with photons. So once again, the electron passes through both the holes. It interferes with itself because these are single electron experiment. That is the beauty of this Tonomura experiment. It is the demonstration of single electron buildup. Ek electron gas, then one electron, another electron, and then another electron. And that produces the interference pattern. So the electron passes through both the holes at once. It is described by a wave function psi, as I had, which is finite here and finite here. It interferes with itself to produce a probability distribution like this. So where will it land up? When you measure, it is either one electron or one photon or one neutron. Never half of an electron. So it does not become half and half. So therefore, it establishes that electron or proton or photon or neutron or alpha particle, they are neither particles nor waves. Not the particle hand, not the waves head. They are described by the Schrodinger wave function. So if you have a single photon source, one photon or the other, and you have a partially reflecting mirror. So 50% is reflected, 50% is transmitted. So you will say, normally anyone will say, that if there are 1,000 photons coming in here, then about 500 will be reflected, 500 will be transmitted. That's the wrong answer. That's the wrong answer. The correct answer is a single photon is described by a wave packet here as well as here. ये यहाँ भी है और यहाँ भी है. Single photon. It is here as well as here. It can interfere with itself. But if you make a measurement, then it is either here or there. Chalo. Similarly, if you have a tunneling through a barrier, some of you must have read, I have a single particle like a proton or neutron or alpha particle coming in, and then there is a reflected wave packet and a transmitted wave packet. So a single particle like proton or alpha particle is described here, is described by a wave packet which is here and here. So it is here as well as there. It may be millions of kilometers apart. But when you make a measurement, then it is listen to every word. When you make a measurement, the wave function, which is here and there, it collapses to being either here or there. Where will it collapse? No one can predict. So quantum mechanics is probabilistic in nature. So this is a photograph of a young girl with 3,000 photons. You have 3,000 spots and 28 million spots. So they are governed by probability. One of the most beautiful and easy to understand experiments which will tell you that quantum mechanics is governed by probability is your simple radioactivity experiment. Let us suppose I have this as a radioactive source like cobalt. It emits, cobalt disintegrates to something or uranium or something like that. Let us suppose its half-life is 1 day. Then what will you say? That if there are 10,000 nuclei, about 5,000 will decay in 1 day. But which 5,000? There will be nuclei which will stay on for days, and identical nuclei which will decay in the next minute. Which one will stay? Which one will decay? God cannot predict. If God could predict, then quantum mechanics will be not valid. But quantum mechanics is correct. It is the most correct discipline of science. So therefore, David Bohm, iska kitab I had shown you the book. The most fundamental theory now available is probabilistic in form. Classical mechanics is deterministic in form. And he is widely regarded as one of the best quantum physicists of all times. This side. So electrons do not, this is Feynman. Oh, you people, we are all very fortunate. You see, when I was at Cornell, I left Cornell before Feynman gave those beautiful lectures. So go to YouTube and listen to the Feynman's Messenger lectures. They are beautiful lectures. One on gravitation and one on quantum theory are just outstanding. You must all listen to that. Whatever I have done today is there. And probably you will not trust me, but when you hear Feynman, then you will say that he is telling the truth. So he says electrons do not behave like particles. They do not behave like waves. Electrons in orbit are not somewhat like, these are his own words, are somewhat like a cloud or fog of some sort surrounding the nucleus. It behaves like nothing that you have seen before. Well, there is one explanation. Electrons behave exactly the same way as photons. So, and then he says, I think I can safely say that nobody understands quantum mechanics. What aspect of quantum mechanics does no one understand? How the electron passes through both the slits at once. Something like that. So these are the references that I had shown you before. And this is where whatever I have done today is given in this optics book. Einstein in 1917, oh my God, it is 11:20. For the rest of my life, I will reflect on what light is. And then in 1951, 4 years before he died, all the 50 years of conscious, read this carefully, all the 50 years of conscious brooding have brought me no close to the answer to the question, what are light quanta? Of course, today every rascal thinks he knows the answer, but he is deluding himself. So I do not know what the truth may be. I'm an old storyteller. I tell you the tale as it was said to me. What I would like to tell the younger generation is that physics or mathematics or any other subject is one of the most beautiful subjects. I'm 82. I still enjoy reading basic physics books. So spend your time in understanding, teach, do well, work hard. Don't work hard, work very hard. Then and then only you will succeed. So then and then only you will be happy. So what is happiness? I always say happiness is when you do something that you enjoy. Everyone wants money. I also want money. That is not bad. But what you try to do it honestly, with integrity, and with a purpose. Read, whether you are a teacher or a student. If you are admitted to Central University of South Bihar or Delhi University or IIT or some college, you are very fortunate. Because 30% of India's population is still below the poverty line. That is a staggering 400 million people. So we are all very, very fortunate. I consider myself to be very, very fortunate to be associated with an institute like IIT Delhi. So consider yourself to be very fortunate that you are able to study. Because how do we remove that poverty? Only through science, technology, and education. So teach people. Today, sitting in Delhi, I can teach people in a remote village in Bihar or Odisha or Rajasthan or Tamil Nadu. So that is the technology. So we are very, very blessed. Chalo. Oh, 11:23. Thank you very much, Sanatan, Dr. Mishra,
Thank you so
and
much, sir.
everyone else.
Thank you, sir.
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 Thank you, sir. Thank you so much.
Chalo.
So thank you, sir.
Namaste, sir.
Thank you
Thank
so
you,
much
sir.
for this wonderful lecture, and
Ah.
especially for your message at the end that you gave to the younger generation. And in the lecture you started right at the beginning, where this renaissance in the modern science actually began
Yes.
by observing and understanding light, and culminated into this beautiful theory that is quantum mechanics, which is supposed to be the most fundamental theory that we know until now. And we are also thankful to you for letting us peek into your educational background. It was really titillating to know that Professor Hans Bethe and Professor D.S. Kothari and Professor Majumdar are among your teachers. And also it was mesmerizing to know about the miracle year of science for Einstein, that is 1905, and how that shaped the development of quantum theory, and also how his genius was treated in the backdrop of that ongoing politics at that time. Also, thank you very much for explaining the fundamentals of quantum mechanics and emphasizing its probabilistic nature. So now we have some questions.
I will read out the question. I am a
Okay.
little tired. I'm an old man. so let me read out the question, and let me see what questions I would like to say. Okay. Thank you. Interactive station is still remaining. Everyone kindly wait. And is it possible to get classical Maxwell's equation from a quantum perspective? No, you cannot get. You see, quantum electrodynamics is already there. So you quantize Maxwell's equations and you get the concept of photons. That is the quantum theory of radiation, which was put forward by Dirac in 1928 or 29, 2 years after the discovery. So first it was Maxwell's equation, which is classical, electric and magnetic field. Then you quantize it. There's a quantization of field. That is entirely a new, entirely different subject. And quantization of fields. And then you introduce the concept of the photon. So Soumashri Das Adhikari writes, so what is the final answer, that light or electron is particle or wave? So that is what I have been trying to tell you. It is neither a particle nor a wave. It is neither a particle nor a wave. Then what is it? It is described by quantum theory, by this probabilistic quantum theory. And in the non-relativistic domain, it is the Schrödinger equation. So you see, listen to this, that, for example, I have written a book on quantum mechanics. That is mainly my non-relativistic quantum mechanics. The entire field of non-relativistic quantum mechanics is just the solution of the Schrödinger equation. Whether it is the scattering theory, or whether it is the hydrogen atom or helium atom or perturbation theory, you spend your lifetime in solving the Schrödinger equation. The spin of the electron comes from the top. So what you may ask me is that you have written down Schrödinger equation, you say that it cannot be derived. Why should I believe it? The reason why you believe it is because it agrees with experiment. It agrees with experiment. And you add to the potential energy term the fine structure interaction. That is, or the hyperfine structure. Hyperfine structure is magnetic moment of the electron interacts with the magnetic moment of the proton, which is at the nucleus. And so they produce an energy. And you see the hyperfine splitting of Balmer series or something like that. Why the Sujit Sahu writes, why the uncertainty is system independent, system dependent. It is not system dependent. Whenever you have an experiment, like the single slit experiment, whenever you try to localize the electron within a distance delta B, say distance B, then it automatically transfers a momentum, which is h by p. Who transfers the momentum? The slit. Is there a conservation of momentum? Of course there is conservation of momentum. There is a recoil. And this is very beautifully explained. Very beautifully. You must read the third volume of Feynman lectures. Third volume of the Feynman lectures. How Schrödinger equation came to his mind? That's a very good question. You must read the paper by Schrödinger. You see, Niels Bohr had given a model of the hydrogen atom. And he had introduced the concept of the angular momentum to be quantized. MVR is equal to NH by 2. So people started wondering, how did he write that down? How did you justify that? So you have to have, when the wave nature of electron was discovered, then people realized, or the wave particle duality was discovered, then people realized there must be wave somewhere. So then Schrödinger was a mathematician. He was about 39 years old when he wrote that paper, or 40. And he said that I must try to get a wave equation. And he didn't use the method that I have given. I have given a very simplistic method. He wrote an Iconol equation and he somehow derived it. And then in 2 consecutive papers, he wrote down the solution of the hydrogen atom problem. Because he was a brilliant mathematician. And so he completed the entire quantum theory in 1926. He wrote 3 papers. And then, of course, Heisenberg also wrote and things like that. Oh, what do you mean by optical tweezer? Oh, that's another story. You see, you have a tweezer. Tweezer is what? You hold diamonds, small pieces of diamond with the tweezer. So you take viruses and you hold them with a light beam, because light consists of photons and the photons have momentum. So you take two light beams. This is a beautiful experiment, and you hold them from all sides, a virus. So that is an optical tweezer. In Young's experiment, why slit is more effective than pinholes? Oh, slit slit is more effective because it will give you more light, and so therefore much more better contrast between the dark and the bright photon. So if you read my book on optics, I have tried to explain that with two pinholes you get a almost straight line interference pattern. Actually they are hyperbole, but they are not hyperbole strictly. So they are hyperbole strictly. So if you look at a small portion, it's straight line. Now you replace the pinhole by slits, then what will happen is each point will give rise to that. So you will have a greater intensity. Chalo, Sanatan, questions ka to koi ant nahi hai. So you people take over, Puneet, and answer the only question. That's it.
Okay, sir. Sure, sir.
Okay?
Yes, sir.
Okay.
Okay. Sanatan. So,
Sir, am I audible?
Yeah, you are audible.
Yes, sir. So we can move to the vote of thanks section.
Yeah, sure.
Yes. I would like to invite Dr. Nitin Chandra, sir. Professor.
Let me
Yes, sir.
answer one more question. Tathagata Bhattacharya has written, is 3D harmonic oscillator explained by JWKB approximation? The answer is JWKB approximation or the variational method or the perturbation method are approximate because you cannot solve the Schrödinger equation in all cases. Only in handful of cases, only for the hydrogen atom I can solve. So you require approximate methods to find the solutions of the Schrödinger equation. So JWKB approximation, Jeffreys, Wenzel, Kramers, and Brillouin approximation is one of the approximate methods. So it is not that it is explained by 3D harmonic oscillator. There is a harmonic oscillator can be solved exactly. E is equal to n plus h half h cross omega. And if you have a three-dimensional oscillator, it is n1 plus n2 plus n3 plus 3 by 2 h cross omega. And the wave functions are Hermite-Gauss functions. So that is the rigorous solution. So it is not explained by JWKB. They explain all the explanations come from the solution of the Schrödinger equation. Okay, that's it. Sorry.
Thank you, sir.
Chalo. Vote of thanks.
Yes. Yes. I would like to invite Dr. Nitin Chandra, sir, Faculty Department of Physics, Central University of South Bihar, for vote of thanks. Nitin, sir, over to you.
Thank you, Mann Vivechan team. And first of all, let me thank the Mann Vivechan team itself because they gave me this opportunity to be here and give the vote of thanks. Because it's not, I think everyone may understand that it's not just any formal lecture, but it's quite a personal experience to all of us because not only you students, but also we as a student, when we were a student, we were actually following sir's classic book. So this time he himself is here and talking to us. It's quite, it's completely different experience. Even now we actually follow his book when we teach in the class. But then I think all of us agree that when we teach the same thing, that experience, and when the expert himself teaches the things, that experience is completely different. So let me thank Professor Ajoy Ghatak for to be here and talk to us. It's a completely different experience, a very personal experience to all of us. And let me thank the organizers also to organize such type of talks, and I think it will be quite good if when the university opens, then we have the such lecture in offline mode. If he be able to physically present in our university and talk, will be quite good. Yeah.
Yeah,
And
I have to visit Gaya someday, so I would like to come.
yeah. Thank you, sir. And yeah, so let me thank participants also, because they only make the things quite interactive because of their questions. So, and also thank everyone. Thank you.
Thank you, sir.
Thank you.
Thank you everyone for joining the session. And now the session officially comes to end. And we have upcoming session on 30th January. So all of you can register to that session. Registration link is open for that. Thank you, sir.
Thank you so much.
Thank you, sir.
Thank you very much.
Thank you, sir.
Thank you so much, sir.
Everyone.
So much, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
All of you now can leave the meeting.